Good morning, students. Welcome back to experimental stress analysis class. And today is class 4 of module 3. And today we'll be discussing about two-dimensional photoelasticity. See, in two-dimensional photoelasticity, we will be discussing the behavior of two-dimensional body which is subjected by stresses. Under two-dimensional, we need to determine the principal stresses which is acting in the member, and due to these principal stresses which has been developed in the member, we need to determine by using certain techniques. So, in the analysis of isochromatic patterns, it was shown that the principal differences between sigma 1 and sigma 2 could be determined directly, and that of maximum shear stress which could be determined provided that the two principal stresses are of opposite sign. Also, we had that the free boundaries, the principal stress and normal stress to the boundary is 0. Hence, the isochromatic data yield directly to the value of other principal stresses, that is sigma 1 and sigma 2, whereas at an interior region of the model, the individual values of the two principal stresses cannot be obtained directly, but from the isochromatic and isoclinic patterns without using supplementary data or employing any numerical methods. See, for this one, we have the isoclinic, since we have discussed that the analysis of isochromatic and isoclinic, which shows that the principal stress difference sigma 1 and sigma 1 minus sigma 2 can be determined, whereas the maximum shear stress can be determined by only the principal stresses. Then the principal stress normal to the boundary is 0. So to obtain this one, we have certain techniques, and those techniques, either it may be a separation techniques. See, where here in this separation techniques, we will be determining the individual values of sigma 1, sigma 2 by using some techniques which are called as separation techniques. So, the separation technique, see, many techniques have been proposed to determine the individuals values of sigma 1 and sigma 2, that is principal stresses. Such techniques which are commonly used are listed below, that are use of lateral extensometer and the use of at any free boundary conditions, and by using Laplace equations, and by using shear difference method. Along with this one, we can use the oblique incidence method. Now we shall discuss the individual techniques, that is the stress separation techniques. The first one we will be discussing about the use of lateral extensometer. Here in the lateral extensometer, it depends upon the Hooke's law. See, for a plane state of stress, we know that the plane strain equations, that is epsilon x is equal to 1 by E into sigma x minus mu into sigma y, and sigma y is 1 by E sigma y mu into sigma x, and similarly sigma epsilon z is equal to minus mu by E into sigma x plus sigma y, where sigma x and sigma y are the normal stresses, and epsilon x, epsilon y and epsilon z are the three strain equations which can be determined. Suppose If the value of the height of h is the original thickness of the model, that is depends upon the thickness of the model before being stressed, let us consider, and after before considering before applying the stress or before stress, let us consider the original thickness of the model as h, and after stressing, the model will be having an amount of the thickness as h plus delta h, which is the thickness after loading. Then strain along z direction can be taken as delta h by h, that is change in thickness divided by original thickness. Suppose if the change in thickness can be determined, then a knowledge of Poisson's ratio and Young's modulus of the model material will be enabled to determine the summation of two normal stresses, that is sigma x plus sigma y. And from the previous equation we can rearrange, that is our two normal stresses, that is sigma x plus sigma y is equal to minus e by mu into epsilon z, that is equal to minus e by mu into delta h by h. So here the instrument that is used to determine the change in thickness, it is the change in the lateral dimension of the model, which is called as the lateral extensometer. Now since sigma x and sigma y, sigma x plus sigma y and sigma x minus sigma z are known values, the individual values of sigma x and sigma y can be calculated. And alternatively also we have sigma 1 plus sigma 2 is equal to sigma x plus sigma y, and sigma 1 minus sigma 2 are known, which are nothing but the sigma 1 and sigma 2 can be determined. Now look into the sketch here where the body, for a stressed body, the stresses for a free boundary conditions. Here at the free boundary conditions we have, when the body of the model is not able to load directly, which is called as free boundary. Suppose the normal and shear stresses on a plane tangential to a free body is 0, then the principal stress axis and normal and tangential of the body. So here the principal stresses acting will be normal to the body. Since you can observe in the sketch here, sigma 2 is a normal stress which is acting normally to the surface of the body, and sigma 1 in the direction of the body axis we can consider it as sigma 1 is equal to sigma 2. Second method we'll call it as the shear difference method. In the shear difference method, this is a step-by-step integration process method. Here in this method, the step-by-step integration process along a selected line starting from a point where one of the normal stress is known. Generally we know that the initial point here, the initial point which lies on the boundary where the individual values of sigma 1 and sigma 2 are known. So here from the sketch you can observe a two-dimensional body. For an entire body we will be considering a small section, and let that section be about a thickness of delta x, the width as delta x, and the total thickness as delta y. And by considering its central axis we will be determining what is the stresses, what is the normal stresses and shear stresses developed in the body. Now for this sketch, this method makes us of one of the differential equation by equilibrium equations. So the equilibrium equation can be written as dou of sigma x by dou x plus dou into tau xy by dou y is equal to 0. Also, we can rearrange the above equation or rewrite the above equation as dou of sigma y by dou y plus dou of tau xy by dou x is equal to 0. See, in the absence of the body forces, the line of integration, which is called the x and y axis, which joins the points of intercept, then whichever the point it is intersecting, where the individual values of sigma x and sigma y are known, then we need to assume that this line is called as x-axis. See, that is what you have written here. The line of which is a x-axis, that is on integrating the previous equation, the above equation, we have the reduced form, that is integral between I to j dou of sigma x by dou x into dx is equal to minus integral of I to j dou of tau xy by dou y into dx. Or we can represent the equation as sigma x of j is equal to sigma x of I minus integral of I to j dou tau xy divided by dou y into dx. Using the finite difference method for the above equation, we can write the normal stress equation as sigma x of j is equal to sigma x of I minus summation of I to j delta tau xy divided by delta y into delta x. Therefore, the values of delta tau xy by delta y are calculated from the values of tau xy, which are determined along two lines, that is C and CD and EF, which are delta y by 2, and these are the two parts which can be divided from the line of integration. That is, line of integration in the sense it is an x-axis. Now for the two lines C and D, let us consider let theta be the angle between the tangent to the boundary and the x-axis. At the boundary, one of the principal stress, let us consider it as sigma 2, will be 0, and the other stresses, that is sigma 1, tangential to the boundary, can be evaluated or can be determined from the isochromatics. Then from the equation, in the previous equation, we can write sigma x of t is equal to sigma 1 into cos square theta. Sigma 1 into cos square theta. Then by considering this one, we can determine the normal stress which is acting perpendicular to the surface, and by this one we can determine the principal stresses which is developed, that is sigma 1, first principal stress, which is developed in perpendicular direction of the loading, can be taken as sigma x of t is equal to, that depends upon the thickness, is equal to sigma 1 of t into cos square theta. This is the second method. Third method is the oblique incident method. Here, so far, the incident ray in the previous we have assumed to be a normal to the face of the model. But if the incidence is not normal, then it is said to be an oblique incidence. Now, in this sketch, you can observe a two-dimensional body which has been tilted by an angle of phi of the ray which is passing through the member. Now, for the entire body, we will take an element of the body that is in terms of two-dimensional bodies. For this two-dimensional body, let the incident ray be in the xy xz plane, and let phi be the angle between the z-axis and the incident ray. For normal incident along the z-axis, the stresses which cause the photoelastic effect are sigma x and sigma y. Then the principal stresses sigma 1 and sigma 2 corresponding to these stresses, however, can be represented by experiments which reveal that the oblique incidence, the stress components which cause photoelasticity effect, are not the primary stresses. Hence, the method can be determined by considering the primary stresses sigma x, sigma y and tau xy. Then the secondary stresses, which can be considered as the rectangular stresses or rectangular stress components corresponding to the direction of incidence. Then the principal stress corresponding to the secondary rectangular stresses components are called as secondary principal stresses. Now, for these secondary principal stresses, which are being denoted by the principal stress 1 and second principal stress, that is sigma 1 and sigma 2, can be represented as sigma x plus sigma y by 2 plus or minus root of sigma x minus sigma y by 2 whole square plus tau xy square. So this is the secondary principal stresses equations, that is sigma 1 and sigma 2. Now, from the figure, we have the transformation of stresses. You can look into the sketch here. The transformation of stresses which induces the equation as sigma x dash is equal to sigma x into cos square phi and sigma y dash is equal to sigma y and tau xy is equal to tau xy into cos phi. Hence, we have the principal stress equation sigma 1 and sigma 2 can be written as sigma x cos square phi plus sigma y by 2 plus or minus root of sigma x cos square phi minus sigma z whole square plus tau x square into cos square phi. Now, similarly, for the incidence along the y direction, we can consider sigma 1 is equal to sigma x. Now, in this method, the most important thing is for the direction ZO, you can look into the sketch here. ZO, the stress vectors which lie completely in a plane perpendicular to ZO, and sigma x dash, sigma y dash is equal to sigma y. And also from the sketch, for incidence along the y-axis, the appropriate stress component is sigma x only. This is what, since sigma z and tau xz are 0 for a plane stress case, which indicates for an incidence along the x-axis, the appropriate stress component is sigma y. Therefore, which are called as the secondary rectangular stress components. And finally, the secondary principal stresses for the oblique incidence we have written as sigma 1 comma sigma 2 is equal to sigma x dash plus sigma y dash divided by 2 plus or minus root of sigma x dash minus sigma y dash by 2 whole square plus tau x dash y dash square, and hence the principal stress equation can be written as sigma 1 comma sigma 2, that is equal to sigma x square sigma x into cos square 5 plus sigma y by 2 plus or minus root of sigma x cos square 5 minus sigma z by 2 whole square plus tau xy square into cos square 5. This is about the third method, that is a oblique incident method. See, this method is only implemented if the incidence is not normal, then it is said to be an oblique incidence. We'll go for the next topic, that is model to prototype scaling. See, the model to prototype, whatever the sketches we will be considering, the model to prototypes in an application, see the model to prototype scaling which has been found in a major applications. See, in the application of photoelasticity method of stress analysis, it is assumed that the prototype structure behaves as a linearly elastic structure within the range of the loads. So for this reason, many of the two-dimensional elements or two-dimensional bodies which has been stressed have been considered in terms of a prototype model. And here in this prototype structure, the behavior of the structure is assumed as a linearly elastic behavior within the range of the design loads. So the model, the photoelasticity model reproduces elastic behavior both at room temperature as well as stress freezing temperatures. See, this stress freezing temperature and stress freezing technique you will be discussing in the next module, that is three-dimensional analysis of the three-dimensional photoelasticity model. Now, when we look into the governing equation of the mathematical theory of elasticity, which shows that for a singly connected body, these are entirely independent of the elastic constants. Let us consider the elastic constants as Young's modulus. One is the Young's modulus E, and along with that one, the other elastic constant as Poisson's ratio of the material. And in absence of the body forces, or when the body force field is uniform, when the body fold is uniform, as in case of the there is what gravitational field. In other Poissons, in other case, suppose if the Poisson's ratio does not have a small effect, even in the case of multiple connected bodies. So in these conditions, what we see, also if the forces around individual openings are such that the resultant force in each case is 0, then the stress distribution remains independent of the elastic constant. So it is possible in most practical cases to apply the photoelastic model result to the prototype. So here there are different methods to determine the prototype scaling, and here we have the first one, which depends upon the scaling of stresses and deflections. See, the stresses and deflections we need to scale up depending upon the physical model to a prototype model. Now, for a two-dimensional structures, the first method is scaling of stress and deflection. See, for a two-dimensional structures, the most significant dimensionless ratio is the ratio of sigma h L by P, and for the deflection we can consider delta h by sigma h or delta L by P, where sigma is the stress at a point and the delta is the displacement at the point, and P is the applied load. And let us consider h as the thickness of the model, and L is the typical length or the typical dimension of the model. Suppose if the load P and M, the suffixes, that is P and M refer to the prototype. P indicates the prototype and M indicates the model respectively. We may write the scaling equation relation for the following stress equations. That is, where we can represent the prototype stress for a prototype sigma P is equal to P of P, that is PP, that is a prototype load by P, PP by PM into HM by HP into LM by LP into sigma M. That is what, again I repeat it, sigma P is equal to PP by PM into HM by HP into LM by LP into sigma M, where PP indicates the load on the prototype and PM indicates the load on the model, and HM indicates the thickness of the model and HP indicates the thickness of the prototype. And now similarly, the displacement in the prototype can be written as delta P is equal to PP by PM into EM by EP into HM by HP into delta M. So here, where delta P is the displacement for the prototype. Now if the pressure or the stress or the pressure sigma naught on the body is defined rather than the load, we have the relation as sigma P is equal to sigma naught P plus sigma naught M into sigma M. Similarly, the sigma P can be written as summation sigma P can be written as sigma naught of P by sigma naught of M into EM by EP into LP by LM into delta M, where EM is the Young's modulus of the material of the model and EP is the Young's modulus of the prototype. Now this is what the scaling for the stresses and the deflection. Sigma P, where sigma P is the scaling for the stress and the delta P is the scaling for the deflection, which depends upon the both prototype as well as the model. This is the first method in scaling from model to prototype scaling. The second method is the scaling of temperature. See, the scaling of temperature here, the thermal stress problems, which depends the scaling of temperature will be majorly for all the thermal problems. So in thermal stress problem, it is generally considered in two parts. That is what we have. If the temperature change delta T is known at all the points and the coefficient of thermal expansion alpha is given in a linear structure, we have for plane stress sigma P is equal to EP by EM into sigma P by sigma M into delta TP by delta TM into sigma M, where again here delta P is the difference in temperature for a prototype and delta Tm is a difference in temperature for model. Now for a straight for the strain for the state of strain, the right hand expression is to be multiplied by 1 minus mu m into 1 minus mu p, where mu is the Poisson's ratio of the model, and similarly the other part is to determine the temperature at any point at any time t. Suppose if A is equal to K by Pc, which denotes the diffusivity, where A is the diffusivity of the material, where K is the thermal conductivity, and rho is the density, and C the specific heat of the model, then the time scale is given by Tp is equal to Tp square, that is for the model for the prototype, Tp square by Tm square into Am by Ap into Tm. This is the equation where we are scaling the model to prototype by considering the temperature fluctuations or the temperature history problems. The third one is scaling for dynamic cases. See, in elastic materials or in elastic system, the dynamic analysis is to determine the frequencies in the system. Suppose here in an elastic system, the frequency n of any specified natural mode depends on the length L that indicates the size of the system. Then the mass density rho of the material and the Young's modulus E is considered, then the most general form of a two-dimensionally homogeneous equation, which can be written as Np is equal to Lm by Lp into Nw, or this equation which will be dependent upon the frequency when the same material is said to be for model to prototype. Then the natural frequencies can be determined, where Np is the natural frequency for the prototype that depends upon Lm by Lp into Nw, and Nm, where Nm is the natural frequency of the model and Np is the natural frequency of the prototype. And here in most of the general what you call as cases for a dimensionally homogeneous equation, the variables are dependent upon the natural frequencies n as well as the lengths, and which leads to the model called as law of frequency. So the above equation which depends upon the law of frequency. These are the three major categories under scaling of model to prototype stresses, that is a scaling of model to prototype. So these are the major things which we need to be considered for scaling of different what you call as models from model to the prototypes. In the next class we shall discuss about the remaining session, that is the remaining part of this two-dimensional bodies or two-dimensional photoelasticity, that is two-dimensional photoelasticity applications, and along with the applications we will be determining what are the different materials that are used for photo, that is the proper materials as well as properties of a photoelastic material. Thank you.